Good morning to all. For today's discussion, we are going to talk about the lessons or the continuation of the lesson that we have last week, which is all about in search of negatives under Module 1 in the second quarter. So this lesson is anchored in the division made module from SDO Caloocan. The most essential learning competency is to explain how the quantum mechanical model of the atom describes the energies and position of the electrons. The expectations are the following. Number one, predict the probable location of the electrons in an atom. Number two, describe and write the electron configuration of the given elements. Number three is to describe and complete the set of quantum numbers for each given element. And number four, supply the following data from the electron configurations such as the period number, group number, and number of valence and core electrons. So last week we discussed about the atom and its subatomic particles. Atoms, as we all know, is the basic building block of all matter, and it has three subatomic particles, which are the electrons, protons, and neutrons. So electrons are the negatively charged particles, while protons are the positively and neutron having no charge. We also tackled about the atomic theories proposed by John Dalton, J. Thomson, Ernest Rutherford, and Niels Bohr. But today, we are going to focus on the fifth atomic theory entitled quantum mechanical model, which are developed by Louis de Broglie, Erwin Schrödinger, and Werner Carr Heisenberg. So quantum mechanical model define the atom as having a central nucleus surrounded by electrons located in the regions with high probability, and it is known as the electron clouds. So the clouds is most dense when there is a high chance of finding the electron, but the cloud is less dense when there is a low probability of finding the electron there. So in quantum mechanical model, we studied that there are four sets of quantum number which will describe the electrons inside the atoms, and they are the N, L, Ml, and Ms. But before anything else, let's have a recap of the four sets of quantum number because they are the highlights of our lesson today. So the first quantum number is the principal energy level and represented by the letter N, while the second quantum number is used to designate the sub-levels, which was symbolized by L. The third quantum number defines the spatial orientation of each orbital and represented by Ml, and the fourth quantum number defines the spins of the electrons. So if there is energy level as the first quantum number, there's also sub-levels under this principal energy level. And we are going to talk about more about these quantum numbers. So this second table presents the main energy level and their sub-level. Okay? So as you can see here, we have n is equals to 1. What does it mean? It means that it is the first energy level. So the n here symbolize the first quantum number or simply the energy level. Okay. While the 1, 2, 3, 4, 5, 6, 7 represent in what particular level is that. When you see 1, meaning it is first. When you see 2, that is the second energy level. 3 refers to third energy level. 4 meaning fourth energy level. 5 pertains to fifth energy level, and so on and so forth. And as you can see on the right side of the main energy level, there are letters. What are these letters? These are what we call sub-levels. If there are main level, there are sub-levels also. So in the first energy level, there is only one sub-level, and that is S. In second, there are two sub-levels which are S and P. And in the third, there are SPD sublevels. In the fourth energy level, we have SPD and sublevels. In the fifth, we have SPDF again, sublevels. In the sixth, there are three sublevels, which are the SPD. And in the last one, we have SNP sublevel. So let us talk more about this SPDF. What are these? We have what we call the type of sublevel, and how many orbitals are there in each sublevel, and also how many electrons can occupy those sublevels, plus how it looks like. So I will give you example later. So take a look at this. There are four types of sublevels, which are the S, the P, D, and F. So we have S sublevel, P sublevel, D sublevel, and F sublevel. So in S sublevel, there is only one orbital, while in P, there are three orbitals. In D, we have five orbitals there. In F, there are seven orbitals. So how about the electrons? Before we go to this column, let me remind you that in each orbital, there could be two electrons only that can occupy the space. So a maximum of two electrons can fill the space in each orbital, meaning to say it will not exceed 2 per orbital. So if we have one orbital, like in the S, the number of electrons that can occupy the space in the S will only be 2. It could either be 1 or 2, but it will not exceed 2 because there is only one orbital there. In one orbital, there could be a maximum of 2 electrons only. How about in P? As you can see, we have three orbitals here. So meaning to say, a maximum of 6 electrons can occupy the P. Why 6? Because there are 3. In each orbital, there could be 2. So 3 times 2, it is equal to 6. How about in D? Can you guess how many electrons can occupy? Yes, it is 10, because it is now 5 orbitals present in D sublevel, meaning to say in each orbital there could be 2. Since we have 5 multiplied by 2, equivalent to 10 electrons. In F, we have 14 because we have 7 orbitals here. So as simple as that, you have to multiply it by 2, because 2 is the number of maximum electron that can occupy each orbital. Okay, so as the orbital increases, the number of electrons that can occupy those orbitals also increases. Okay, so how it looks like. Take note that this figure that I will show you is just a representation. For instance, a box represents the orbital. So one box is equals to one orbital. So the arrow here represents the electron. One arrow equals to one electron. So, like what I've said, in the S, there is only 2 electrons maximum of 2. So, in our drawing, we can only draw 2 electrons like this. How about in P? How many orbitals? There are 3. So, 1, 2, 3. So, we have 3 orbitals here. So, we are now going to present the electron. 1, 2, 3. So we are going to draw the arrow up first before arrow down. That's the rule. So 3, 4, 5, 6. So as you can see, in each orbital, there is only a maximum of 2 electrons in each orbital. Okay? 2 only. So it becomes 6 because we have 3 orbitals here. How about in D? We have 5, so 1, 2, 3, 4, 5 orbitals. And since we have 5, we can now draw the arrow which represent the electron. So arrow up first, 1, 2, 3, 4, 5. Then arrow down, 6, 7, 8, 9, 10. In the last F sublevel, we have 7 orbital 1, 2, 3, 4, 5, 6, 7. 7 orbitals. How about the electrons? 1 arrow up, 2, 3, 4, 5, 6, 7. Then arrow down, 8, 9, 10, 11, 12, 13, 14 electrons in the F sublevel. So as you notice, the orbitals increases, the electrons also increases. And as you notice also, as you observe, we have to write down first the arrow up, and we have to complete all the orbitals before writing down arrow down. Because there are certain rules and principles that we have to follow in drawing, in making a diagram about the orbitals and electrons of the given element. So I hope it is clear to you, and you have to follow the rule. So let us see, how are the electrons positioned in the orbits, and what are the rules and principles that I'm talking about that we need to follow in diagramming the orbital of the following elements. Here are they. First in line is the up-bow principle, which states that electron enters orbitals of lowest energy level. We have s orbital, p, d, f. We have 4 orbitals, the s, p, d, f. And the lowest of all is the s orbital, having 2 electrons. As you remember, s has 2, p has 6, d is equals to 10 electrons, and f maximum of 14. Another principle is the Pauli's exclusion principle, which states that an atomic orbital may describe at most 2 electrons. Either 1 electron or 2 electrons can occupy the orbital, but they should be in opposite spins. One is clockwise and the other one is counterclockwise. Opposite meaning one is arrow up and the other one is arrow down, like this. I said that these boxes represent the orbital, and each orbital can have a maximum of 2 electrons, so we have to write the electrons inside with opposite spins, clockwise, which is represented by arrow up, and counterclockwise, which is symbolized by arrow down. And Hans' rule, on the other hand, states that when electrons occupy orbitals of equal energy, one electron enters each orbital until all orbitals contain one electron with spins parallel to one another. So this rule is the reason why we must draw the arrow up first before arrow down. We have to fill up all the orbitals before we proceed to the counterclockwise spin. Okay, take a look at this. One orbital, so arrow up, then arrow down. So this pertains to the s orbital because it has one orbital only. Another s orbital, one, and then down. How about in p orbital? There are 3 orbitals there. 1, 2, 3. So let's apply Hans' rule here. So according to Hans' rule, the electron should enter all orbitals before going to the next spin. So one electron enters each orbital until all orbitals contain one electron. So we have to fill up all the orbitals before we go to the next spin of the electron, like this. Arrow up, arrow up, arrow up. Then it is complete. We can now proceed to arrow down. Clear to you? I hope it is clear because we are going to apply these principles and rules in the succeeding lessons and exercise. So take a look at this and always bear in mind. The center of the atom is what we call the nucleus. Okay, take a look at this. And the first orbit is what we call first energy level, which is represented by n is equals to 1. So the n here is the first quantum number or the principal energy level. The number 1 refers to the level, is it first, second, third. In this moment, we have the first energy level. That's why it is written as n is equals to 1. Okay? And in n equals to 1, we have s sublevel. In the second orbit, that is equals to the second energy level, which is n is equals to 2 and having s and p. In the third energy level, it is n is equals to 3 because it is third, and then the sublevels inside the third are the s, the p, and the d. In the fourth one, it's represented by n is equals to 4. We have s, p, d, f. So in the next orbit, it is the fifth energy level, which is equals to n is equals to 5, and we can see there the s, p, d, f sublevel. In the sixth orbit or the sixth energy level, which is represented by n is equals to 6, the sublevels are s, p, and d sublevels. And in the last one orbit, we have n is equals to 7 because it is the seventh energy level. The sublevels are s and p. Okay, so this is the diagram representing the nucleus and the orbits, the 7 orbits where the electrons are moving around the nucleus. So basically, the electrons are outside the nucleus, while inside the nucleus you can find the proton and neutron there inside. Outside, here are the nucleus moving around or orbiting around the center. Okay? So, in each orbit, you can see S, P, or D, or F sublevels, or a combination of the 4 sublevel, depending upon what sublevel is the first, second, third, fourth, fifth. So, this will be your guide as we go on out to our topic today. Next in line, let us see now how to apply the quantum numbers on the given element. And this is the highlight of our lesson today, how to assign quantum numbers of electrons in a given element. There are certain steps to follow. The first one is to identify what element or elements is or are given. For instance, we have boron and nitrogen as the given. So what will be the second thing to do? Step 2 is to check the number of electrons of the given element in the periodic table. So meaning to say, periodic table will be an important tool for you to arrive at the correct answer in the exercise that we are going to have later. So the boron here and nitrogen, how many electrons are there in our given? So it is very important that you have your periodic. So let us check our periodic table. For the boron, 1, 2, 3, 4, 5. This is the boron. The fifth element in the periodic table. So meaning to say, if it is fifth element in the periodic, the atomic number is 5 and the electron number is also 5. How about the nitrogen? The nitrogen is the seventh element in the periodic table, meaning the atomic number of nitrogen is 7, the electron is also 7. So since we now know what are the electrons of nitrogen and boron, we can now proceed to the third step, which is writing down the electron configuration of the given element. We have to write first the electron configuration of boron. But in doing so, take note that third step is one of the crucial steps in identifying the quantum numbers because as you can see, there are several steps that we have to focus on. The first one is to identify the quantum number, to identify or to write down the electron configuration of the given element by this pattern. So this pattern of electron configuration is the one that we are going to follow. So just be guided with the flow of the arrow here, the flow. So you have to follow the flow so that you will arrive at the correct answer. Okay, so take a look at this. The coefficient 1 here refers to the energy level. So if you see 1, meaning first energy level. If the coefficient is 2, that is second energy level. If the coefficient is 3, meaning third energy level, and so on and so forth. Here, the letter represent what type of orbital is that. If you see S, meaning S sublevel. If you see P, P orbital. Or D, D orbital. F, F orbital. We only have 4, the SPDF orbitals. And the exponent naman, the exponent here represent the number of electrons that an element have. For example, here you can see 1, meaning 1 electron only. If you see 2, 2 electrons, 3, 3 electrons. If the exponent is 4, meaning 4 electrons, okay? So the coefficient pertains to energy level. The letter represent the orbital, and the exponent refers to the number of electrons. Clear? Okay, example, germanium. Germanium is symbolized by Ge, having 32 electrons. So meaning to say, more electrons, the longer the electron configuration like this. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p2. And this is the atomic orbital of the germanium with 32 electrons. So it is very long because of the high amount of electrons. So for you to visualize how this electron configuration go, let us start with an element having small amount of electrons like lithium. Lithium, as you will look at your periodic table, is symbolized by Li. And the electrons that lithium have is only 3. Okay? So look at your periodic table, you can see Li there. And it is 3. 3 atomic number, meaning 3 electrons. So how are we going to write down the electron configuration of lithium? Simple as this, just follow the pattern. Let's start with 1s2. 1s2. What is next to 1s2? That is 2s. So you have to write 2s. So the problem is, what is the exponent for 2s? Is it 1 or 2? Reminder, in s orbital, we can only have a maximum of 2 because s orbital has only one orbital, which is equal to 2 electrons only. So since we have 2 now, for this electron to become 3, we only need 1 electron more. So instead of writing 2, we could write 1 so that if you will add 2 and 1, it is equals to 3. Okay, so take note that the exponents, the summation of the exponents should equal to the electron number of the given element. Another example, fluorine. Look at your periodic table. What is the symbol of fluorine? Let us check our periodic. Here we can see the F. F is the symbol of fluorine, and if you will count it, it is the 9th element in the periodic table. So meaning F9. Okay, so at the electron configuration, let's start with 1s2 again. Only 2. We cannot write 3, 4, 5, 6 for the S because S has a maximum of 2 only. What is next? Following the arrow, we have 2s. What is the maximum electron of S? That is 2. Okay, 2 plus 2 is equals to 4. And we need We need 9. So we have to move on with the arrow, and the next one is 2p. P. So the maximum number of electrons of P is 6. But if we are going to write 6 here, it will equal to 10. And we only need 9. So instead of writing 6, we could write 5. So if you are going to add 2 plus 2 plus 5, it is now equal to 9. And 9 is the atomic or electron number of fluorine. Take note that the exponents pertains to the electrons like this. So I have reminders a while ago that the exponent refers to the electron number of the element. Okay, another example to make you understand. Potassium. Let's find the potassium in the periodic table. What do you think? You have your periodic table, YouTube. What do you think is the atomic number of potassium? It is symbolized by letter K. And if you will count it, potassium is the 19th element in the periodic table. So, K is the symbol and 19 is the atomic number. Okay, let's start again with 1s. The maximum is only 2. So we have to proceed to the next one. 2s. Maximum again is 2. So moving on is 2p. P, the maximum of p orbital is 6. So 6 plus 2 plus 2 is equals to 10. So we need 9 more. So going back or moving on 2p, then we have now 3s, maximum only of 2. So we need more to make it 19. 3s followed by 3p. Maximum is 6. So 2 plus 2 plus 6 plus 2 plus 6 is equals to 18. And we have or we need 19. So let's proceed to 4s. S, the maximum of S is 2, but we will not write 2 because it will exceed 19. So instead of 2, we have to write 1. So that if we will add these exponents, 2, 2, 6, 2, 6, 1, the equivalent number is 19, which is the potassium element. Okay, gets? So that is the way you have to write the electron configuration of the element. The first thing to do is to look at your periodic table to check how many electrons are there, and then follow this format: 1 is to 2 is to 2p, 3 is to 3p, 4s, so that you will arrive at the correct electron configuration. But take note that in each orbital, there are maximum electrons that orbital can hold. For the S, maximum of 2. For the P, maximum of 6. For the D, maximum of 10. And for the F, maximum of 14. I hope you get it because you are going to use this information for the succeeding exercises. So before going back to the steps, let's have a seat work first so that I may know who are the students who gets the idea of electron configuration, and I hope you can apply this in our seat work 1, which is giving the electron configuration of the following elements. So beryllium is the first, followed by oxygen, magnesium, then phosphorus, and the last one is chlorine. So I will give you 5 minutes to do this, and after that, if you're done with your seat work 1, you can send it to me through Messenger, and then I will request that you will present your work. Okay? But after that, I will give also the correct answer. Okay, your 5 minutes starts now. Okay, time's up. Let's have the answer. For beryllium, we have 1s2, 2s2, because beryllium is fourth element. Oxygen, we have 1s2, 2s2, 2p4, because oxygen has 8 electrons. Magnesium is 1s2, 2s2, 2p6, 3s2, equivalent to 12 electrons, while phosphorus is 1s2, 2s2, 2p6, 3s2, 3p3, which is equals to 15 electrons of phosphorus, and the last one is chlorine, 1s2, 2s2, 2p6, 3s2, 3p5, equivalent to 17 electrons of chlorine. Okay, so we're done with the electron configuration. We can now proceed to the steps. After that, we can now write down the electron configuration of boron. 1s2, 2s2, 2p1. For nitrogen, we have 1s2, 2s2, 2p3. So 5 electrons, 7 electrons. The fourth step is to draw the orbital diagram of boron and nitrogen. So again, we have to separate these steps so that we can focus in orbital diagramming of the specific element. How about the orbital diagram? How are you going to do that? Here, let's start with boron. So boron is the fifth element in the periodic. So following this pattern, we could have 1s2, 2s2, and 2p1. So the exponents summation are equal to 5. So for 1s2, in our table, we can see that S refers to one orbital. So the exponent pertains to the electron. So we are going to draw arrow up, then arrow down. So if you will count it, this is 1, 2. So 2 electrons. So this is the orbital diagram of 1s2. How about 2s2? Since it is S, we have one orbital only, and then 2 electrons. The electrons will be represented by an arrow. Arrow up first, then arrow down. So this is the orbital diagram of 2s2. How about 2p1? So p orbital, how many orbitals are there in p? We have 1, 2, 3 orbitals. And the exponent is only 1, meaning only 1 electron. So draw an arrow to represent the electron. Arrow up. So there's no arrow down, there's no electron next to it because it is only one electron to make it 5 electrons in the boron. How about nitrogen? Nitrogen is symbolized by N, having 7 electrons, 1 S2, 2 S2, and 2 P3. So for the 1 S2, since it is S, one orbital only. So arrow up, arrow down. In 2s2, again it is S, so one orbital only, but 2 electrons, so arrow up, arrow down. In 2p3, since it is P, we now have 1, 2, 3 orbitals. And 3 electrons, you have to fill all the orbital first, so arrow up, arrow up, arrow up. So 3, 1, 2, 3. So these arrows represent the 3 electrons in the 2p3. All in all, we have 1, 2, 3, 4, 5, 6, 7 electrons for the nitrogen. So there you go. That is the orbital diagram of the boron and the nitrogen. Okay, it looks like this. As you can see, one arrow here because it is 5, 3 arrows to make it 7. So this is the electron configuration, and this is now the orbital diagram. Let's have the last step, which is writing down the 4 quantum numbers in the given element. So this is the final step. So how it looks like. Before proceeding to the next or final steps, let's have sheet work number 2, and that is to give the orbital diagram of the following elements like beryllium, oxygen, magnesium, and phosphorus and chlorine. Again, 5 minutes will be yours to finish your sheet work number 2 and just send to me the photo of your work. Your timer starts now. Time's up. These are the answers for your sheet work number 2. Beryllium, oxygen, magnesium, phosphorus, and chlorine. So check your work so that you can have your score today. Let's proceed to the next one. The 4 quantum number. The first given element is the boron with 5 electrons, and its electron configuration will be like this: 1s2, 2s1, 2p1. So after writing down the electron configuration, we can now have the sets of quantum numbers for boron. So since we have 5 electrons for the boron, we can now write first electron, second electron, third electron, fourth electron, and fifth electron until fifth only because it is 5. How about the first quantum numbers? So this is how the quantum numbers of boron. Electron configuration. We have to draw the atom and the orbits where the electron can move. That's why electron configuration play a significant role here, and using this diagram, we can be able to write the electron configuration of boron. So the center part is the nucleus, and around the nucleus, we can find the first orbit, which is n is equals to 1, and also known as the first energy level. In n is equals to 1, you can find the 1s2 there. The 1s2 is located in the first energy level. Okay, in second energy level or in the second orbit, it is n is equals to 2, wherein 2s2 and 2p3 are located. 2p1 are located rather. So the 1s2 is in the first, 2s2 and 2p1 are in the second energy level. So reminder, n is the energy level, and 1 or the number 1 or 2 refers to the first or second energy level. So that means that n is equals to 1 is what we call the first energy level. N is equals to 2 refers to the second energy level. Again, the 1s2 here having 2 electrons, we can say that it is 2 electrons because of the exponent. It is located in the first energy level or n is equals to 1. In 2s2, we can say that there are 2 electrons because of the exponent. It is positioned in n is equals to 2 according to our drawing, or in the second energy level. Our 2p1 here is located in the second energy level, which is n is equal to 2, having 1 electron only because of the exponent 1. So simple as this. Nucleus, first orbit or first energy level, we can find 2 electrons there. 1 is 2, meaning 2 electrons because of the exponent 2. The second orbit, or the n is equals to 2, how many electrons are there? As you can see in the electron configuration, we have 2s2 and 2p1, meaning 2 plus 1. So meaning there are 1, 2, 3 electrons in the second orbit or second energy level. So I am emphasizing the n is equals to 1 and n is equals to 2 because that pertains to our first quantum number. Okay, so this is the first electron, the second electron, the third electron, the fourth electron, and fifth electron of boron. So take note, where are the first and second located? Are they are they in the first or second orbit? How about the third and fourth and fifth electron? Where are they? Are they in the n is equals to 1 or n is equals to 2? Because you are going to answer that for you to complete this table in the first quantum number of boron. So first and second electron, as we see in the diagram, it is n is equals to 1, n is equals to 1. While the third electron is positioned in the second, the fourth in the second, and the fifth in the second. How about in the second quantum number? Okay, another crucial part of quantum numbers. So we have to use this table for the value of L, M, ML. L is the second quantum numbers, and ML is the third quantum number. As you see, if L is equals to 0, ML is equals to 0. Meaning to say, there are equivalent values of L and ML to each other. If L is equals to 1, the values of ML increases and there are 3, negative 1, 0, and positive 1. If L is equals to 2, the values of ML are negative 2, negative 1, 0, positive 1, positive 2. If L is equals to 3, the values of ML are negative 3, negative 2, negative 1, 0, positive 1, positive 2, positive 3. So, how can we explain this? Using this table number 2. So as you see, in the right side of L, there are S, P, D, F. And as you remember, S, P, D, F are what we call orbital or the sublevel, the S orbital, the P orbitals, the D and the F orbital. In each orbital, there are a specific number of quantum numbers there. For example, if the orbital is S, the value of L is 0. If the orbital is P, the value of L is 1. If the orbital is T, the value of L is 2. And if the orbital is F, the value of L is 3. Okay? So, we have S, P, D, F. What is the connection of ML to L? There are big relation between the two. Let us see. Using this figure, you can be able to detect how many orbitals are present in the SPDF because it has something to do with the ML. So in the S, we only have one orbital represented by one box. In the P, we have three orbitals, so 1, 2, 3. In the D, we have 5, 1, 2, 3, 4, 5 orbitals. And the F has 7 orbitals. 4, 5, 6, 7 orbitals. So again, how are these orbitals related to ML? Because it will it will give us or it will reflect what are the ML values. For example, in S, it is one orbital, so it is equals to 0. P orbital, so we have to use the integer. First is negative 1, 0, positive 1. Okay? So when you see P, it will equal to negative 1, 0, and positive 1, talking about ML. In the D, we will start at negative 2, negative 1, 0, positive 1, and positive 2. And in the F, we have negative 3, negative 2, negative 1, 0, positive 1, positive 2, and positive 3. So, this is much more easy for you to remember why it become negative 1, 0, positive 1, negative 2, negative 1, 0, positive 1, positive 2, because it pertains to the orbital. When you see S, 0. When you see P, you have to use three integers. If it is D, you have to start with negative 2. If you see F orbital, you have to start at negative 3 and end up in positive 3. Okay, so this is very important in identifying the first, second, third quantum number of the given element. So the first energy level or the first electron of the boron is located in the S. So we can say that L is equals to 0 because it is S. How about the second electron? The second electron is still S. So meaning L is equals to 0 still. The third electron now is in the S, so L is equals to 0. The fourth electron is in the S, so L is equals to 0. And the fifth electron now is in the P, so L is equals to 1. So the values of L has some equivalent values to ML or the third quantum number. As you see in the previous table, so this table will help you to give the third and second or the LMML quantum number. So let us apply this table to complete the ML for the given element which is the boron. So for the boron, we have now the second quantum number The third quantum number is represented by ml. So if L is 0, the ml is also 0. So the same, because L is 0. But in the fifth electron, L now is equals to 1. So ml will be different and it is equals to negative 1. The fourth quantum number has something to do with the atomic orbital or the orbital diagramming like we did a while ago. So we have 1s2, this is the orbital, 2s2, this is the orbital, and we have 2p1, so we have 3 orbitals for the p. So arrow up, arrow down for the 1s2. Arrow up, arrow down for the 2s2. And only arrow up for the 2p1, one arrow only because there is only one electron left in the 2p1. So if it is arrowed up, it is positive 1 half. If it is arrowed down, that is equivalent to negative 1 half, or clockwise, counterclockwise, counterclockwise. So here in the first, this is the first electron, the second electron, the third electron, the fourth electron, and the fifth. In the first electron, we have positive 1 half because it is pointing up. In the second electron here, it is negative 1 half because the arrow is going down. The third electron is represented by this arrow, so it is positive 1 half. The fourth one is going down, so negative, and the fifth one is arrow up. That's why it is positive 1 half. So there you go. We have completed the quantum numbers of boron. But of course, I will give another example, and that is the nitrogen. This is the, we have to start at the electron configuration of nitrogen. So for the nitrogen, it is represented by N having 7 electrons. The configuration will look like this: 1s2, 2s2, 2p3, and draw the table having first electron, second electron, third electron, fourth electron, fifth electron, sixth electron, and seventh electron. Until 7 because nitrogen has 7 electrons. So the first quantum number, we have to look at the atomic distribution of electrons. So first, we have to follow this format to attain the configuration of 1s2, 2s2, 2p3 for the nitrogen. And then draw the nucleus as the center part of our atom. And then the first orbit is n is equals to 1, meaning first energy level. And you can find there the 1s2 configuration in the first. In the second orbit, which is represented by n is equals to 2, you can find the 2s2 and the 2p3. Okay, so here 2s2, 2p3. Reminder that n is equals to energy level, and the number itself refers if it is first, second, third energy level. So this is just a clarification and a reminder. So here, the 1s2, this 1s2 has 2 electrons because of the exponent 2, and it is located in the first energy level, which is represented by n is equals to 1, and the 2s2 having 2 electrons are positioned in the n is equal to 2 or second energy level, and the last configuration of 2p3 having 3 electrons are located in the second energy level, which is n is equals to 2. So simple as this, let us distribute the electron. First is the nucleus, the first orbit. How many electrons are there in the first orbit? We have here in the first 2. So we have 1 and 2 electrons. In the second orbit, which is n is equals to 2, how many electrons are there? According to our diagram, we have 2p2 and 2p3. So 2 plus 3 is equal to 5. 1, 2, 3, 4, 5 electrons. Okay? So this drawing will help you analyze and will help you answer the first quantum number because this electron pertains to the first electron, second electron, third electron, fourth, fifth electron, sixth, and seventh electron of the nitrogen. So the first orbit, meaning n is equals to 2, The second orbit has 5 electrons, n is equals to 2. So take note of the following information here because you have to rewrite the n is equals to 1 for the first electron of the nitrogen. Second, n is equals to 1. The third electron is positioned in n is equals to 2. The fourth is in the second. The fifth is in the second. The sixth electron is in the second. And the seventh is in the second energy level. So again, we need to use this table to answer the second and third quantum number, the L and the ML. So L is 0 if it is S. L is 1 if it is P. L is 2 if it is D. And L is 3 if it is F. And the ML values pertains to how many or what are the values of L. If it is 0, 0. If the L is 1, we have negative 1, 0, positive 1. So you have to use this to complete the table for the nitrogen. Okay? So let's have the second quantum number of nitrogen. Since it is S, the L is 0. S again, L is equals to 0. This one, the third and fourth is in the 2s. So S, it is 0. L is equals to 0 because it is the S. And the fifth, sixth, seven, the last three is in the 2p3, meaning it is the p orbital now. So L is equals to 1, L is equals to 1, L is equals to 1. So if L is equals to 0, ML is equals to 0. ML is equals to 0. So there are equivalent values of L, there are equivalent values of ML for the values of L. Now, in the 2p3, we have p orbital, that's why L is equals to 1. So you have to use the integers now starting from negative 1, followed by 0, and then positive 1. Okay, yes? In the fourth quantum number, we have positive 1 up, negative 1 up, positive, negative 1 up, positive 1 up, positive 1 up, positive 1 up. So why it looks like this? Because of the atomic orbital of the nitrogen. So the 1s2, this is the orbital of 1s2, this is the orbital of 2s2, and this is the orbital of 2p3. S, that's why it is 1 orbital. So P, that's why it is 3 orbitals. So you have to draw the arrow, arrow up, arrow down, arrow up, arrow down, arrow up, arrow up, arrow up. Following the Hans rule, you have to fill in all the orbital first. So that is the reason why it becomes 3 arrow up. So if it is up, the equivalent value is positive. If it is down, it is negative. So first electron, second, third, fourth, fifth, sixth, seventh electron. So up meaning positive 1 up, down negative 1 up, positive 1 up, down negative 1 up, positive, up, positive, up, positive, up, positive. Okay, so again, we have completed the quantum numbers of the second given element, which are the nitrogen. So it's time for you to try it on your own. So this is your last sheet workup for the day. Try to give me the electron or the set of quantum numbers of the element lithium. So I will give you or I will provide you the configuration and the orbital diagramming of the 3 electrons present in the lithium. 1s to 2s1, meaning there are only 3 electrons for the lithium. Again, 5 minutes is your time to finish this. Just send me the picture of your answer and you may start now. Okay, time's up. Let us see the answer. For the first electron, n is equals to 1, L is equals to 0, ML is equals to 0. In the second energy or second electron, n is equals to 1, L is equals to 1, and ML is equals to 0. In the third electron, we have n is equals to 2, L is equals to 0, and ML is equals to 0. And to answer the MS, you have to draw first the orbital diagram, which look like this. So, first, electron second, and then third. So we have arrow up, positive 1 up, arrow down, negative 1 up, and arrow up, positive 1 up. So just check your work for our sheet work number 3. And before we end up, I will just give you additional information regarding the paired electron of our orbital diagramming. So note, clockwise spin is represented by arrow up. The electron must be the first one to draw, and all orbitals must be filled in first before proceeding to the counterclockwise spin. So, as you can see here, I want to show you the electron configuration and the orbital diagramming of the element lithium, chlorine, and potassium. Okay, so as you can see in the potassium, it is very long because as the electron increases, arrow up, arrow up, arrow up, arrow down, arrow down, arrow down. For the 2p6, how about in 3s2? 3s2 arrow up, arrow down. In 3p6, we have 1, 2, 3, so 6, 1, 2, 3, 4, 5, 6. In 4s1, we have 4, and it only has one electron, so arrow up. So this one is what we call paired electrons. Paired because they are in the opposite spin. This one is what we call the unpaired electron. This is paired. There's a partner, so paired electron. Paired electron, paired electron. The last one is unpaired because it is only one arrow. Paired, 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 paired electron, paired, paired. So all paired except for this, which is unpaired. Okay, so take note of the difference between paired electrons and unpaired electron. So before we end up, I just want to remind everybody of the following tasks that you are going to submit this week. So quiz number 2 in the Google form. Performance task number 2 should be uploaded in the Google Classroom. And module number 1, you already received your module number 1 and it should be uploaded clearly in the Google Classroom. That's all, and I hope you learned something that you can apply in the real life situation.